So we've talked before this video about all kinds of things dealing with functions. In pre-calculus, we looked at such things as being able to find intercepts of a graph, being able to find vertical and horizontal asymptotes, even and odd functions, symmetry, all those kinds of things. And then in calculus, we increased our knowledge of how to graph by adding such knowledge as when do we know where we get a horizontal tangent line, where can we find critical points, maximums and minimums, intervals of increasing and decreasing, and concavity of the function. Well, with all of this knowledge, it would be a shame to waste it without going through and learning how to use all of this information to help us graph. And that's one of the main purposes that we spend our time in derivative calculus dealing with. So that's what we're going to do. We're going to have some guidelines for analyzing the graph of a function. And you can see them here. I've circled it. I've put them in blue. How do we determine what a graph looks like based on the derivative? So, of course, we need to do a few things. And in order of the things that I like to do is that I just go down my checklist, and I very often have to look for the domain and range of the function. Now, the domain is usually a bit easier for us to determine than the range. The range might require us to do a few steps before we come back to determine it, but it is important for us to note something about domain and range of a function for us to be able to use the information to graph the function. Now we want to be able to determine other things, such as we want to be able to determine our x and y intercepts, asymptotes of rational functions or other functions if that happens to be the case, and the symmetry, whether or not a function is even or odd, because that symmetry can be used to show us what the graph looks like. If we know what happens on one side of the y-axis, we know what happens on the other. All of this is what we've learned in pre-calculus. Of course, we want to be able to locate the x and y, the x values for which the first derivative and the second derivative are either 0 or don't exist. Those critical points can be used to identify relative or absolute extrema using the first or second derivative tests as appropriate. And then we can use that information to get a graph. So it'll be worth our time to go through a few examples. And I'm going to start with a graph of a polynomial to help us illustrate all of these guidelines. So here's our graph. We want to analyze and sketch the graph of the function. So we're going to go through the analysis first, and then I'll show you how I use that analysis to generate a graph. It's a very powerful method once you know. So the very first thing, of course, we want to label any intercepts, our relative extrema, points of inflection, and asymptotes on our graph. So here we have f of x equals 3x to the fourth plus 4x cubed. As a polynomial, of course, you know that that makes our domain the set of all real numbers. We've already previously gone through and defined polynomials as being the kind of functions that are continuous everywhere, unless for some reason we specifically change the information. Well, the other thing we need to know is the range. Range of the function, that's a little bit harder. How do we know what the range is? Well, we are going to have to find a derivative, but we can say the following, that right now we know, if you remember from pre-calculus, one thing that we looked at was called a leading coefficients test, and we have a positive leading coefficient with an even degree. This is the positive 3 is the leading coefficient, 4 is the degree, and that indicated to us that it was going to have this kind of end behavior where both ends went towards positive infinity. Well, that's useful. That means, though, that we might come to a minimum somewhere before we head up. Whether or not we head through the x-axis will remain to be seen. Well, intercepts are found by setting f of x equal to 0. So we want to find what those intercepts are. So let's go ahead off to the side here, and how do we find our intercepts? Well, an x-intercept is found by setting the function equal to 0. So we have 3x to the fourth plus 4x cubed. And we set that equal to 0 to solve for x. We factor out x cubed in this particular case, leaving us with 3x plus 4. And then we set each factor equal to 0, and we'll find that at x equals 0 and x equals negative 4/3, we have our points, our intercepts. Now, luckily, if 0, 0 is the x-intercept, that also means it's the y-intercept. So we don't have to go any further in defining the y-intercept. But we find a y-intercept by setting x equal to 0 and then finding the y value that goes with it. So in this case, 0, 0 is our case. Now that we have that information, is it an even or odd function? In this case, no. If we were to substitute in f of negative x, we're not going to find any useful information right here, right? F of negative x does not equal f of x, so it's not even. F of negative x is not the negative of the original f of x, so it's not odd. Therefore, we can't use that. And there are no asymptotes. This isn't a rational function that has that kind of feature. So the next thing we're going to do is look at our derivatives. Well, f prime of x. F prime of x, the derivative, we can just use our power rule. Luckily, this is 12 x to the third plus 12 x squared. All right. Well, if we're looking for critical points right here, we want to find any critical points where the derivative is equal to 0. That's easily enough done here. If we have 12x cubed plus 12x squared, set that equal to 0. Factor out 12x squared right here. That's going to give us x plus 1. And that's going to give us two critical points. X equals 0 as a critical point, and x equals negative 1 as a critical point. Right? These are our critical values. So, of course, we would want to go through and find out what happens at these critical values. We know in the function f of 0 is equal to 0. In our original function, that's here. And f of negative 1, is going to be 3 times negative 1 to the fourth plus 4 times negative 1 to the third. That's 3 minus 4. That's going to be negative 1. Negative 1. All right. Now, because we don't have any other points right here, we might want to use our first derivative test. So what we would do is that we would take our factored form right here. We would identify the points where we have our critical numbers, that's negative 1 and 0, and see what happens to the value of the derivative by doing our positive and negative analysis. So we're going to take 12x squared. We know that 12x squared is positive for all real numbers. How about x plus 1? Well, we can test our intervals right here. If we chose a number to the left of negative 1, say negative 2, we'd have 12 times negative 2 squared plus negative 2 plus 1. That results in f prime being negative. We know that changes to 0 at negative 1. What happens between negative 1 and 0? Well, if we were to put in negative 1/2, negative 1/2 plus 1 is positive. 12 times 1/2 squared is positive. Therefore, f prime is positive there. And then we try a number that's greater than 1. How about positive 1? Well, 12 times 1 squared times 1 plus 1, that would also be positive. So this is the kind of function where it's decreasing, change that here, decreasing from negative infinity to negative 1. It's increasing from negative 1 to 0, and then increasing again. So our first derivative test tells us that if we go from decreasing to increasing, from negative to positive, that means we have a relative minimum here. And so we know that we have a relative minimum at the point negative 1, negative 1. And it doesn't look like there's a relative maximum. Nothing happens at 0, 0. The first derivative test is inconclusive. However, we know that the function is increasing over the interval from negative 1 to 0. We don't know what happens at 0. It's a horizontal tangent. And from 0 to positive infinity. And in the meantime, it is decreasing on the interval from negative infinity to negative 1. Okay, next we look at the second derivative to tell us something about the concavity of the graph. We find f double prime of x. That's going to be 12 times 3, 36x squared, plus 12 times 2, 24x. So we're going to use that to help us find any points of inflection right here. So what we do is we take 36x squared plus 24x, set that equal to 0 to find any possible points of inflection, that is changes in concavity. We could factor out 12x from both terms. That gives us, let's see what that gives us. That gives us 3x plus 24 divided, that's 2. That equals 0. And so that gives us values x equals 0 and x equals negative 2/3. Okay, so what could we tell from this? It looks like we're going to have changes in the sign of our second derivative at negative 2/3 and at 0 possibly. So let's check out what happens. If we check a number to the left of negative 2/3, that would mean that we would have a negative, let's try negative 1. Negative 12 times negative 1 is negative. 3 times negative 1 plus 2, that's negative. That makes this positive. So we've got a concave up shape right here. From negative 2/3 to 0, let's try negative 1/3. If we took negative 1/3 of 12, we would have a negative number. If we took negative 1/3 times 3 plus 2, we'd have a positive number. That means we've got a negative number. And so this shape is concave down on the small interval from negative 2/3 to 0. Then we try numbers to the right of 0. Well, if we tried positive 1, we'd have 12 times 1 times 3 times 1 plus 2. That's a positive number, so it's concave up again. So looks like we have two places where we have change in concavity. Those are points of inflection, and we would substitute those values into our original function. So I substituted in x equals negative 2/3 into my original function, and negative 2/3 there. Substitute that into my original function. F of negative 2/3 turns out to be the number, and you can work this out for yourself, negative 16/27. And another critical number here, as far as our points of inflection occurs at x equals 0. And we know, of course, that f of 0 is equal to 0. So that's another point of inflection. And our points of concavity, our intervals of concavity, we have concave up shape from negative infinity to negative 2/3, and from 0 to infinity. We have concave down on a very limited interval from negative 2/3 to 0. And then, of course, our points of inflection occur at negative 2/3, negative 16/7, and at 0, 0. All right, so what we're going to do is we're going to take a look and see what that looks like. So one way of outlining this is just to put our intervals right here. So we indicated that we had intervals of increasing and decreasing this way. We said that the function would be decreasing from negative infinity all the way up to negative 1. That's decreasing. And then it would be increasing on the interval from negative 1 all the way up to positive infinity, with a little bit of a break there at 0. So that's increasing. We also said that the function would be concave up on the interval from negative infinity all the way up to negative 2/3, right about there. It would be concave down on the little interval from negative 2/3 to 0, so concave down here. And then it would be concave up again all the way off to positive infinity. So concave up, right? We can outline those. We can also plot our points. Essentially, we said we had a minimum at negative 1, negative 1. So let's go down here. Negative 1, negative 1. We said that was a minimum. Negative 2/3, negative 16/27. I'm going to put that right about here as our point of inflection. And at 0, 0, that's a point of inflection, but it's neither a maximum nor a minimum right here. 0, 0. And we said that the graph would pass through the points negative 4/3, which is about negative 1 1/3, and 0. Well, it's time to see what this is going to look like. So let's take our graph and let's see what it looks like if we bring this into the picture. Hey, sure enough, there it is, right? Relative minimum at negative 1, 1, passing through the x-axis at negative 4/3 and 0. Two x-intercepts, two places where the derivative is equal to 0, and hey, we got a great graph.